Okay, so remember when we were talking about improper integrals, and we showed that the integral from 1 to infinity of 1 over x to the p converges to 1 over p minus 1 if and only if p was greater than 1. So if we use this and in conjunction with the integral test, yields that this series, the series from 1 to infinity of 1 over n to the p, will converge under the same condition. So this is called a p-series. If we have p equals to 1, then we have the summation from n equals 1 to infinity of 1 over p, which we know is the harmonic series, which we know diverges. Now, the other important p-series is the one of 1 over n squared. Per the test above, this one converges. However, this series actually it converges to an exact value. Euler in the mid-1700s determined this to be pi squared over 6. Eventually, we will get to that point of being able to prove it, but not until much later. So as we are going through these, the p-series is very, very easy. You are looking for what your p-value is. So in this case, p equals to 3, so this converges. In this case, p equals to 1/2, so this diverges. P equals to 1.01, so this converges. I'm going to go ahead and circle these that converge. Now, what do you think about this series? We're going to be able to state, and we'll talk about this later, but this behaves like 1 over n. I'm going to put the summation in. So this one, we're going to say p equals 1, so it diverges. Now, this next one requires a little bit of manipulation. So we have series from 1 to infinity of n equals 1, and we have e times 1 over n to the pi. Well, p is equal to pi, so it's going to converge. And again, this next one needs some manipulation. So we have the sum from n equals 1. So I can simplify 8 to the 1/3, and that's just 1 over 2 times n to the 1/3. Okay, so our p is equal to 1/3, so this one diverges. And that's going to be the end of the p-series notes.